if that's the case, if such an f and such a g exist, then x and y are homotopic. Which is a weaker condition than, is it weaker? I think it's weaker. I think it's a weaker condition than homeomorphic, right? Homeomorphic implies homotopic. Right, let me just write that. Homeomorphic x and y implies homotopic x and y. But these are not equivalent. All right? Because it's much less greedy. We're not even saying that f and g are inverses. They're just sort of inverses up the homotopy. Right? There's a lot of wiggle room in there in this estimation. However, notice this: if you could show x and y are not homotopic, that implies they're not homeomorphic. So it is useful for making sort of more gross distinctions. Yeah. But what I'm going to spend most of my time talking about in here over the next story arc of class is path homotopy, right? So path homotopy is what it sounds like. It's homotopy of paths. So what is a path, first of all? Who knows? Maybe I'll finish it today. Weirder stuff has happened. I skip enough proofs, we'll get there. So a path is, say, f, a mapping from I, which I to x. This is a continuous, okay? So this gives a path in x, all right? A homotopy of paths, so definition, let's say you have f and g paths in x, right? Then a homotopy of paths is a family f sub t, which is again a mapping from the identity to x, all right, for 0 less than or equal to t less than or equal to 1, such that what? Number 1, the endpoints we have f sub t of 0 equals to x naught, and f sub t of 1 is equal to x1 for all t. And 2, the associated map f from I cross I, and I think usually this is called the homotopy, but he calls it the associated map, which is cool. Defined by, I mean, he's right that the f sub t is really more primary in terms of the intuition, and this is really just a formal construction to capture the necessary continuity between the different members of the family. But this is continuous. I think I need to say a little bit more in terms of the setup here. Right. What has to be true in order for this to make sense? like here's a picture, x naught. Right, here's a picture, x1. Okay? So if I make a picture of f, right, where does it go? I don't know. Like that, perhaps. I don't know, whatever. Okay? And if I make a picture of, I mean, the thing is, when I plug in 0, oh, I guess I haven't gotten to it yet. Well, but for this to make sense, I need that these are coterminal paths. You know, in x, from x naught to x1. Okay? So like both paths, they start at x naught and they go to x1. Yeah? Whatever. There's your G, right? And then, you know, a typical f sub t in between these two, I don't know what it looks like. It could be this, whatever. Right? But as, here's, you know, f sub t, but I guess the punchline here is if f sub 0 is equal to f and f sub 1 is equal to g, then f and g are homotopic. And you can write f equivalent to g. I think I may be messing the notation up. Yeah, he's just got one bar. He's not. It's just that. And all of my other ones should have also been that. I mean, you'll find different notation in different books, I imagine, but I'm trying to follow Hatcher at the moment. Okay. Okay. So that's. But you see, it's exactly this is just a specialization, right, of the general definition to paths, right? The interesting thing here, of course, is that, well, I think one of the interesting things about the path is like there's like a direct connection between the image of the path and the path itself. Like when I have a function from, well, let me not, I don't even know what I'm saying. I'm going to stop saying it. So let me bail on that ambiguous comment. Okay, so how about this? If you have any two paths in Rn, so example. Oh, yeah, I'm sorry, guys. I am not well today, obviously. Hopefully I'm not sick. I don't know. I'm doing stupid stuff today. I'm doing really stupid stuff today. Ay, ay, ay. We're on page 1, so you didn't miss out much. And the definition I wrote on the other board's not in here. I made that up. So, so if you have, you know, if your space is Rn, right, and we've got, you know, from x naught to x1, say, I don't know, I guess we'll call that f naught, right? And then over here, f1, then, so these are both, you know, paths that take domain 0 to 1, right? So you can just use the usual trick, right? Like pick an arbitrary point here, f naught of t, somewhere in there, right? Same one down here, right? Actually, let me call that of s. Let me use s here for that, actually, because I want to use t for the other thing. So you connect these two by the line segment, right? How do I go? That was supposed to be F1. Yeah, thank you. Like I said, good job. So I want to go that way, right? What would the parameterization of that? I'll use a gamma of t for a second here. I do what? I do f naught of s, right? Plus t times f1 of s, right? Minus f naught of s, right? That's the formula for the parameterization of the line segment. You know? And so you just say f sub t of s, right, is equal to what? Well, f naught of s plus t times f1 of s minus f naught of s. And, you know, there's your homotopy, right? F of however it was supposed to go, s comma t apparently. Yeah? Is that continuous? Search your heart. Find it. Surely it's true. Yes. What's that? If there's any justice, right? This doesn't feel like the setup of some unnecessary joke, so it should be safe. It's so needless, too, because that joke demands itself at the start of the next section in the notes, if you think about it. Because the whole next section was, given a map, is it going to be the case that it's a quotient map? So the answer obviously is, if it's not possible that it's the quotient map, it's too late for it to be a quotient map. But yes, this is continuous, and so this shows that any two paths in Rn, coterminal paths obviously, to talk about it, they're homotopic. So homotopy in Rn is kind of boring, right? And this construction, right, do you guys know what a convex set is? What's a convex set? Let's say a convex subset of, you know, we can do it for a vector space, I suppose. Is as x comma y a subset of C for any x comma y in C. So it's stronger than star-centered. It's saying that between any 2 points in your set, the line segment connecting those points is also within the set. This is a convex set. Star-centered means line segments from a given point can reach any point in the set. That's weaker. This is pretty strong. And you see this construction that we just did would equally well work inside a convex set. Right? Because you can just go from, if you have two paths inside the convex set, you know, like this I guess would be convex, right? So if I take two paths in there, I can always just do this exact same construction in that context because the line segment can take connecting, you know, f naught of s to f1 of s necessarily is within the set. So any two paths, any two coterminal paths in a convex set, subset of Rn, are also homotopic. All right. Now we got through page 1. That's good. How late did I start class today?
5 minutes.
5 minutes late. But you guys were here. You guys were here earlier, though. I think I started on time.
Started right on time.
On time-ish. All right. So let me tell you guys where we're going next time. So great. So I need. I'm not going to restate the definition of homotopy next time. All right. So that was unfortunate. So next time we're going to talk about. We're not really so much interested in coterminal paths. We're actually much more interested in loops. That is, paths which begin and end at the same point. All right. So it turns out that we can look at the set of loops and we can define a group structure on them. All right. Actually, they form. There's in like the way to join two groups is like you probably just go one and then go another. There's an inverse to like invert the loop. Instead of going like that, you go like that. It's the inverse to the loop, you know. So there's an inversion, there's the multiplication. It turns out that this is associative. So it is an honest to goodness group. And so this is known as the fundamental group, right? And so the fundamental group usually use like a pi. Pi 1 of x is the fundamental group of x. Is built over this group structure. But it's not done with just paths, it's done with homotopy classes of paths. Because homotopy gives you an equivalence relation on the set of paths, rather set of loops. And this allows us to carefully and technically define the term simply connected. We're going to see that what it means for it to be simply connected is that the fundamental group is trivial. So now pi 0 also has a meaning. That describes the number of path components, if I remember right. But I could be wrong about that. But anyway, this is the fundamental group. It basically, in some sense, judges how circles fit into your topological space. There are also higher homotopy groups, which kind of tell you how larger dimensional spheres fit into the space, up to deformation, something like that. This is, understanding these things deeply is a large chunk of what's called algebraic topology. The other sort of, so there's like, you know, all of these various theorems about homotopy, which we're just gonna just graze over the surface of it. I just want to get you guys to know what the meaning of homotopy is. We're certainly not going to learn the deeper theorems. Just enough so that we can at least give a technical meaning to the things you've seen in other courses, yeah.
So it seems like Rn for n greater than 2 would be simply connected, it seems.
Mm-hmm.
Because you can just avoid the origin.
Yeah.
I guess maybe with like pi 2 of x it would be different. Like, is that what you're saying? Like another, if you put a sphere in there, you can't avoid the origin. Like
Oh, I don't know right offhand how the higher homotopy groups work for Rn.
Okay.
But I'll try to find out. You know, the interesting thing is my wife had a course in mathematical physics at Stony Brook where they actually looked at higher homotopy groups and things. I really regret not taking that class. But there are applications of topology to modern physics. But those things, that's really quite on the cutting edge of physics. Like, it's hard to find that stuff written in a way which is understandable. Anyway, thanks guys. Sorry my 10 minutes went a little bit longer than I